All right, thank you very much. It's great to be here. So I'm going to be talking about work in progress with Jivan Chandra, who is here in the audience as well, on holographic tensor networks in conformal field theory, especially in 2D conformal field theory. I'm going to start out by motivating this problem. Consider a pure state black hole in asymptotically ADS. So pure state black holes, the spatial geometry of such a black hole looks something like this. Out here is the ADS boundary where it opens up. There's an apparent horizon, which I'm going to take these black holes to be time symmetric. So the apparent horizon is a minimal surface on the time symmetric slice. And inside the black hole is some matter supporting this positive curvature here. The red squiggle denotes the matter, like the collapsing star that created this black hole. This isn't a pure state, so rho is psi psi. Now there are two properties that we expect on very general grounds. First of all, since there's a horizon in this black hole, we expect that there's a coarse-grained entropy that can be assigned here, and that the coarse-grained entropy should be a quarter of the area of the apparent horizon. Now the exact quantum state here is pure, so it has zero von Neumann entropy. So the coarse-grained entropy must be something else. It's not the von Neumann entropy of rho. Secondly, we expect what I'll call the isometric transition. And this is something that is now is maybe less well known, but it's been discussed a lot recently. So let me explain what this is. So V is the holographic map. V is a map from the bulk effective field theory to the physical Hilbert space. So it's a map from the low energy theory in the bulk to the Hilbert space of the dual CFT on the boundary. And the point of the isometric transition is that there's a qualitative difference in the holographic map depending on whether things are outside the black hole or inside the black hole. It's an isometric map outside the black hole and non-isometric inside. So an isometry is a map that satisfies this condition, V dagger V is equal to the identity. In other words, V is a faithful embedding of the bulk theory into the boundary theory. And by imposing that it's an isometry, this guarantees that everything that you calculate on the bulk side will agree with the things that you calculate on the boundary side. It's a structure-preserving map. So on the outside, it makes sense to impose this, but the holographic map can't possibly be isometric inside a black hole. The reason for that is just the counting argument involving the coarse-grained entropy. So if we insert, so we can think of this map, for example, as being a map from the state of this matter supporting the black hole in the interior to the CFT Hilbert space at the boundary. So if we insert a bulk field operator inside the black hole, well, there are many different states in the effective field theory that you can put behind the horizon. And in fact, that number of states can be much bigger than e to the s, where s is the coarse-grained entropy of the black hole, or the area over 4. And it's just impossible to have a faithful map V from a big space to a smaller space. In other words, the rank of V dagger V is bounded above by e to the s coarse. One way of thinking about this property and understanding what we should expect for the holographic map when you're behind a horizon is this interesting correspondence between geometry and random tensor networks or other types of holographic, other types of quantum codes. Okay, so the idea here, and generally the idea of the relationship between geometry and random tensor networks, is that when you see a spatial geometry like this, again, this is the spatial geometry, I'm not drawing space-time here. We have a spatial slice. The idea is that the quantum information theoretic properties of this state are in many ways very similar to what you get if you discretize the spatial slice and replace it with a random tensor network. So in this case, I've discretized it and plopped down a bunch of tensors. So these black dots are the tensors. And they're being multiplied together by the contractions indicated by the lines. And the geometry of the tensor network is the same as the geometry of the initial spatial slice. Each of these tensors is a particular tensor. And which particular tensor depends on the bulk matter. So you can think of the holographic map V in this setup as being a map from the labels on these tensors to the CFT Hilbert space that lives here at the edge. The little green legs at the edge, that represents the Hilbert space of the physical theory. And the reason that this gives us some intuition here is that a random map, for a random map, whether it's isometric or not, depends entirely on the size of the Hilbert spaces that it's mapping. So if it maps a small space to a big space, it's automatically approximately isometric. So in this case, if we think of inputting some data into the network here, and then ask how it embeds into the physical legs on the right, then if we're going from small to big, that's an isometric map. If we're going from big to small, it's co-isometric, meaning isometric in the opposite direction, non-isometric. And over here, it's isometric again. So what we expect, based on this picture, is that we should have an isometric map on the outside and co-isometric on the inside. Now, these tensor network pictures are, you should think of this as a toy model. There are many purposes for which thinking about information in this state, this is a useful picture. I'm going to be discussing cases in 2D CFT where something a little bit like this is literally true. So there's an exact formula relating tensor networks like this to 3D gravity calculations, although it will not be a fine-grained network like this one. So the goal is to explain these features of pure state black holes from the dual CFT. I'll mostly do this in 2D CFT, that's where all the explicit calculations are, but I'll come back at the end with some comments on the general story that could apply in higher dimensions. I'll start by discussing why or when you can think of CFT states as random tensor networks, part one. Then, so I'm going to construct these tensor networks. Once you have the tensor network, the nice thing is that now you can there's all this literature on random tensor networks and the relation to holography, and now we can borrow any of that and apply it to this model. So there's various things you can do with these tensor networks. I'm going to tell you about one of them, which is this isometric transition. For the CFT people in the audience, the basic point that we're going to come to is that there's a subtle breakdown of the identity block approximation in the black hole interior, and that's going to be responsible for this isometric transition. So the bulk theory that we're talking about is 3D gravity coupled to massive particles. And we conjectured last year that this theory is dual to an average over 2D CFTs with just a couple of simple properties. First of all, they have to have black holes, so they have a Carty density of states above the black hole threshold. And secondly, they have 3-point coefficients satisfying the eigenstate thermalization hypothesis, or ETH, in the form appropriate to a 2D CFT. So the eigenstate thermalization hypothesis tells you that the matrix elements like this one, when the states are sufficiently energetic, essentially are random. Now, in 2D CFT, there are a lot of symmetries. There are a lot of things that are controlled by Virasoro, so obviously those things are not random. But the appropriate way to phrase ETH in this system is that these matrix elements the matrix elements of primary operators are random. So here, Cijk labels a 3-point function of 3 primaries. And so ETH says that this is random in the sense that I'm going to separate it into 2 terms. The first one is a random tensor Tijk that has 0 mean and unit variance. The second thing is this function C0, which is a known variance that's calculated from Virasoro identity block. Now, in a general CFT, this property, this ETH property, it would only be reasonable to expect this ansatz to be true at asymptotically high energies. But in a theory that's dual to gravity, there are good reasons to believe that this is true, not just at very high energies, but essentially whenever you're near or above the black hole threshold. So this defines an ensemble that we can then average over, because now we can average over this random part. The evidence for this proposal amounts to a long list of examples where it gives the right answer, in the sense that you can do a gravity calculation in the semi-classical limit, including potentially one-loop corrections, and you can compare that to writing out observables in this CFT ensemble and averaging over the ensemble. For example, it reproduces two boundary wormholes. This is a special case, actually, of the type of wormholes that we heard about from Lawrence this morning. It contributes to an average of the product of CFT 4-point functions. There are more complicated wormholes that involve higher topology on the boundaries, maybe higher topology plus particles. These red lines are particles going across the wormhole. There are also examples with a single boundary, but some interesting topology in the bulk. And in all the cases that we've been able to understand and do the calculation on both sides, the bulk 3D gravity answers agree with this average over 2D CFTs. Okay, so what I'm going to basically be rephrasing that in the language of random tensor networks. Let's consider a CFT state, which is just created by inserting some heavy operators inside the unit disk. So this is a state in radial quantization. I'll take these operators to be dual to particles that are heavy enough to back react, but not heavy enough to be black holes. This is h less than c over 24, but greater than 0. The holographic map V in this context is the map from all the ways of inserting these A operators into the CFT Hilbert space. So you can think of it as a map on the flavor indices, not just, well, a map of all the different ways. So on the left, we could have just one operator or 2 or 10 or 100. The map from all the different ways of doing that into the C Hilbert space is the holographic map V. So to understand what this state is dual to, we calculate the norm, and that norm is a correlation function that involves twice as many operators. We have all the A. Here I've done the case where there are 4 A insertions that make the state. That's at the bottom of the sphere in the bra, and then 4 more in the ket. So this is calculated by something that's a bit like a Witten diagram, except that it back reacts. So these particles are heavy, and we have to include gravity, and we get a diagram that looks like this, where the bulk ADS, so this is filled in with ADS3, but it's back reacting from the heavy particles. The geometry on this spatial slice is relatively easy to write down. It's given here. Rho here is the vertical direction, and d sigma squared is the hyperbolic metric on the spatial slices. So if we were slicing it horizontally across here, and rho is vertical. Now to foreshadow where we're going, note that each of these particles is joining with its partner. So if we have an A dagger A appearing in that correlation function, it's joining with its partner in the bulk, and that means in the language of CFT that it's fusing to the Virasoro identity representation, which includes the identity operator and also all the things that you can make with the stress tensor. We're going to have to revisit this equation in a few slides, but this is what it looks like is happening. Now, the metric on the spatial geometry is, in order for this to solve the Einstein equation, the metric on the spatial geometry is the hyperbolic metric. So it looks something like this. Here I've drawn a picture where the 4 operators are all pretty heavy, so they all make conical defects that are quite strong. And then I've drawn the hyperbolic metric on the disk, a cartoon of the hyperbolic metric on the disk with these operators inserted. So this is an example of one of these pure state black holes that I mentioned in the beginning. It has boundary out here, a bunch of matter supporting a black hole, and if that matter is heavy enough, then these will be very pointy defects, and you'll get minimal surfaces like the ones that I've drawn here in blue.
Are these operators orthogonal?
Sorry?
Are these operators orthogonal?
Yeah, these are primary operators. Different primary, well, yeah, different primary operators, yeah. The question is whether they're above the multi-twist threshold. Let's see. I don't know. In general, I'm not assuming that. I'm going to talk about cases where some of them are light, but in this picture, they're probably all above the multi-twist threshold. Yeah. Okay, so we're going to write this CFT state as a random tensor network by doing the OPE. We do this, first we just do the standard OPE. We take the operators 1 and 2 and fuse them together into a representation P, and so on with the other operators. Here I've just written that OPE out. There's some OPE coefficients. There's a primary, there's a representation R that's the final result of doing all these OPEs. And then there's an operator called the Virasoro OPE block that adds the descendants. Okay, so the role of this thing, this is an operator that takes you from primary states and adds descendants to them. And it's completely determined by the Virasoro algebra. So far, this is exact. Now we're going to use some approximations. This is going to land us on the random tensor network. So first, we're going to use large central charge. So in the large central charge limit, if this state is dual to a black hole, then this sum is dominated by a saddle point. And what I really mean here is that when you calculate the norm, that norm is dominated by a saddle point in the sum, and that's the saddle point that I'm talking about. The fact that this is dominated by a saddle point allows me to bring this Virasoro OPE block out front. So it's not true in general, but at the saddle point, this can come out of the sum. And that's the first crucial thing that we need to turn this into a tensor network, as we're going to see in a second. So we can pull the Virasoro OP block outside of the sum. Secondly, I'm going to assume the eigenstate thermalization hypothesis in the way that I just explained. And that means that these OP coefficients here become known weighting factors times random tensors. At that point, this is just manifestly a random tensor network in the following form. So I'm indicating here with the star that we've truncated near the saddle point, and each of these tensors is associated to the random coefficients that appear in the eigenstate thermalization hypothesis, and the final tensor on the right is the OPE block that adds the descendants. Okay, and this is a random tensor network. It's important that not all of the lines on this network are the same. The internal lines on the network are labeled by primaries. In this case, they're finite dimensional because we've truncated near the saddle. Okay, so each of these internal lines is a primary near the semiclassical saddle. This double line notation at the end of the network indicates a physical CFT state. So the internal lines are primaries, the external line is a physical state. Yeah.
Can you say something more about the saddle point? Just a computational norm of the state?
Yeah.
But if I took the inner product between two different states?
Yeah, we could talk about that saddle too.
But would that be the same tensor network or a different?
That would be, it would look the same, but we would be truncating it to a different, each of these is a truncated tensor, so it would be a different network. So the claim is that this tensor network discretizes the radial direction in the bulk. And this is a precise quantitative statement in the following sense. Well, first of all, it is designed to have the right norm, so the norm of the states agrees with the bulk. That's by construction. Secondly, the bond dimensions in this tensor network are e to the area over 4, where these are the areas of the different pieces of the bulk. Okay, so if we superimpose this over the bulk geometry that we started with, each of these nodes is representing a region between the extremal surfaces of the bulk geometry. Okay, so it's not a fine-grained tensor network like that one with all the tensors I drew at the beginning. It's a much much larger scale tensor network, but it's one that's precise in the sense that it really gives the answers of 3D gravity. Yeah. This is the area in Planck units. Yeah. Yeah. Yeah.
Is the radial direction, there is nothing canonical about the way you did the OPE. You did 1, 2, and then 3. If you are associating somehow the radial direction with that ordering, is that right?
Yes, that's right. And there are crossing transformations that tell you that the true network cannot be exactly random. Okay, because in order to, if you expand it a different OPE, you get a different answer. So crossing symmetry actually constrains how random it can be, but I don't know quantitatively how to include that at this point.
When you say radial, you sort of have in mind that you're going from the infrared to is there some sense like that? Because that's what we normally would associate with the radial direction, that it's you're going towards the infrared as you go in the radial direction. Is there something like that in the CFT? I'm just trying to understand in what sense that radial direction you're mapping to this.
I'm not sure what you mean. Let's see. So I mean, the geometry literally looks like this. So there's a natural radial direction. I guess you're saying that there are different ways of slicing it. This is going to be related to the isometric transition. So maybe you can ask me after we talk about that. Okay, so the third property, the quantitative check here, is that the probes undergo this isometric transition at the horizon, and that's what I want to describe now. Over primary dimensions, yeah.
Where's the saddle?
Where does it well, for the pictures that I'm drawing, it lands in the black hole regime. They're all landing in the black hole regime. But now I'm going to talk about an example where, well, sorry. These are also landing in the black hole regime, but this one's going to be a little different. No, just somewhere in the middle. Somewhere. Yeah, yeah. We could consider a case where one of these minimal surfaces pinches. And that, I think, is a really interesting limit because it's like a black hole singularity, but I'm staying away from it. So this tensor network, I'm going to show, realizes and extends a proposal that was made by Berlinian collaborators in a series of papers. So for this discussion, and generally for the discussion of where the black hole horizon is, we want to talk about probe operators. Okay. In fact, if you just look at heavy operators, there doesn't seem to be anything particularly special about the black hole horizon. We want to look at probes. And so I'm now going to take the same tensor network, the same picture, and take one of the operators to be a light particle. Okay, so to be concrete, I'll just have 3 insertions. So I have 2 heavy ones making the black hole, and then an operator O, which is dual to a particle phi, that's a massive particle inserted somewhere in the bulk geometry. The tensor network for this is the same as before. There's some random tensors associated to the OPE coefficients, and then an OPE block that gives you the CFT state. Now, as I discussed in the beginning, in a random tensor network, the isometric or non-isometric behavior of the code is determined entirely by the dimensions of the bonds. So now that we've phrased this in the language of a random tensor network, we just have to consider the bond dimensions, and we can use that to understand whether the code is isometric. Therefore, the CFT makes the following prediction. I'm going to try to stick it on one slide here and put it all together. So it makes the following prediction. If we take the norm and expand in these conformal blocks, there's a saddle point that dominates this conformal block sum. And the prediction is that the holographic map is isometric if and only if at the saddle point the bond dimensions are increasing as you go along the conformal block. Okay, so for this to be isometric, so these primary weights are determining the bond dimensions in the tensor network. And therefore, in order for that tensor network to be mapping from small to big, we need these entropies to be ordered small to big. Crucially, it's the primary energies that appear in this relationship, not the total energies, and that's necessary to get a quantitative match to the bulk. That's essentially because only the primaries are the random part of the theory. If we had talked about energy eigenstates, let's say, instead of primaries, then I suppose we could still make a tensor network, but it wouldn't be a random tensor network. We're trying to get a random tensor network because then the properties of the network are reflected in its geometry. Another way that you can say this is that if the map is non-isometric, then the Virasor identity approximation must break down. That is, these operators ODAG, or this operator O, the probe operator, cannot give you ODAG or O is 1. Now, this breakdown is subtle because it can only be detected in complicated superpositions. There's no reason, it can still give the right answer for this correlation. It can and does still give the right answer in this correlation function, and it can give the right answer in 1,000 correlation functions. But if we consider complicated superpositions of these external operators, it must break down. So that's the difference between an isometric and a non-isometric code.
Geometrically, does this happen when there is a geodesic behind the horizon that has a smaller length?
No, it's when the probe, well, that's what we're about to talk about. It's when the probe goes behind the horizon. So, so now we get to the non-trivial test. This is the bulk test of this claim. We must show that this transition occurs exactly when the particle crosses the apparent horizon of the black hole. Yeah.
Can you say one more time why the bond dimension is exactly dependent on the weight of the property? I thought it was related to the horizon itself.
Well, from the CFT point of view, it was constructed by truncating this state at the saddle point, so it's given by the entropy there. From the bulk point of view, it should be the area. I haven't described that calculation, but that's a check that needs to be done, and it is also given by the area. And that comes from the same calculation that I'm describing here. It's both the primary weight in the CFT and the area in the bulk. Good? Okay. Okay, so the code, it should be isometric outside, non-isometric inside. And so we should be able to see that in the conformal block expansion or in these primary weights in the random tensor network. And so here's briefly the steps of the calculation are that this is a bulk calculation. You start from the bulk geometry. From that, you read off the stress tensor and the dual CFT. Then there's a prescription that we learned from, there's a prescription due to the Zamolodchikov to turn that stress tensor into the weights into the primary weights appearing in the OPE. It's not as simple as just integrating it to get the energy. That would be the total energy. There's a more complicated monogamy prescription for doing that, and that gives us the saddle point weights in the block. The conclusion of this calculation is that it works in the sense that the transition happens at exactly the right point. As you take this particle in the bulk and you move it across the horizon, then the transition occurs from isometric to non-isometric. These black holes are complicated black holes. They're not spherically symmetric. They're not time independent. So there's a whole complicated curve here that describes that apparent horizon. and it works anywhere along that curve. Yeah.
In that context, would anything special happen with the event horizon? You said no.
No, yeah, nothing special happens at the event horizon as far as we know. Yeah.
So what does it mean from the CFT perspective about only inside horizon or not? You have to look at these forward functions?
If we look at this, from the CFT point of view, it means that these operators can fuse the identity inside this correlation function, but not inside all such correlation functions. So like if we take superpositions of these, let's give these a label, A1, AI, AJ, and make superpositions, then you can find superpositions where the identity approximation breaks down. That's the statement in CFT. Because there's an entropic obstruction to having these fused to the identity in all possible external states.
But which ones work and which ones don't translate into this statement about whether it's inside the horizon or outside the horizon?
No. No. The distinction is when you're outside the horizon, they fuse the identity truly in arbitrary states. And when you're inside the horizon, it can only happen, they can only fuse the identity in a limited set of states.
So do you think the thing that dominates in some is the heavy states instead of the identity? So the identity still appears and the heavy states is relevant?
No, let's see, in this channel, everything is always heavy. I just mean that if you were to look at the fusion of the two O's, the question is whether these two O's can fuse to the identity in the channel where you bring them together first.
Can you say a bit more how it showed up in the calculation? You make the position sufficiently complicated?
Yeah, okay, so basically there's just a counting argument. It's the same as the counting argument we did in the bulk, that if there are more states, now these are all infinite dimensional because we're doing CFT, but we've already found that it's dominated by a saddle point and there's only a certain set of important states here. If there are more states here on this leg than here, then it can't possibly be true that there's another channel where O and O fuse to the identity. Now, it can still seem true in the sense that it can still give the right answer for this correlation function. And that's the weird thing that happens, is that it still gives the right answer for this correlation function, but it's impossible for it to be true in all possible superpositions of these states. You have to be able, just by counting, you can find states formally. I mean, you can't literally write them down, but you can prove that they exist, that there exist states in superpositions where the identity approximation breaks down.
Are you basically saying if I go to the other channel and everything's diagonal by one, the Q will be, the intermediate state will be the same as the T, and if the Q is bigger than the T, then I can't use this approximation?
It's about whether P is equal to R. The question of whether they fuse the identities is whether P is equal to R. I don't know if that answers your question.
Well, I thought you wanted to bring in over Q, or Q doesn't play a role.
Well, in the other channel, there is no Q, because we fused these things. Okay, I have to draw another picture for this, but we would fuse these to the identity would hit here, and we would just compare P and R. I think an interesting question for the bootstrappers in the audience is whether there are other situations where this occurs. Okay, so in the analytic bootstrap, we often are interested in regimes which are dominated by the identity operator, like cone bootstrap, Tauberian theorems. They show up all over the place. And I wonder if there are other situations besides black hole interiors where there's an entropic reason that this approximation must break down. For example, do non-holographic CFTs have an isometric transition? We don't know. They might. They're simply a counting argument. So let me wrap up with some comments. I think I'm going to, since we're running a bit over time, I'm going to skip the comments on wormholes, but let me just say briefly that these tensor networks can be glued together in a very natural way, and that when you glue together the tensor networks, it reproduces the wormholes that I discussed at the beginning. So there's a natural operation on tensor networks that corresponds to this construction of wormholes in the bulk, and they quantitatively agree between the two sides. What about higher dimensions? So, well, we don't have anything quantitative to say, but what should the tensor network look like? So in 2 dimensions, well, in higher dimensions, the right thing to do is not to organize in conformal blocks. Okay? In 2 dimensions, we used Virasoro because it allowed us to separate out the the random chaotic black hole part of the theory from the low energy part of the theory, which in this model was entirely Virasoro. So the analogous thing to do in higher dimensions is not to use conformal blocks, but to somehow separate out the theory into the chaotic part, which is the black hole microstates, and the low energy stuff that dresses those states. And we don't know how to do that in higher dimensions, but roughly speaking, the internal legs on the tensor network should be black hole microstates, and then we dress them by low energy operators. Similarly, to describe higher dimensional gravity as an ensemble average, it seems necessary to first factor out, in this sense, the low energy theory. In other words, we need to understand how to apply eigenstate thermalization in this setting where some stuff is very random and chaotic black hole microstate stuff, and other stuff is completely dictated by effective field theory. We only want to impose randomness on the black hole piece. And I'll stop there. Thank you.
Thanks, Tom. Some time for questions or comments. I will start from back.
Okay, very naive question. So if I have an extremal black hole, from the point of view of the outside, I would have an infinite distance to get to the horizon. So from the point of view of the computation that you're doing for the tensor network, will you see generically for an extremal configuration that you will never have this transition? Is that am I?
Let's see. We haven't thought about that case. I think that extremal black holes probably cannot be prepared on a time symmetric slice. It's important here that we're preparing these states with a Euclidean path integral. No, maybe it can. I don't know. We haven't really thought about how that would go.
Hi, can you expand a bit more on your last comment about figuring out how to apply ETH? I thought what you implied is the sense that we usually use it, right? That like simple or low energy observables in high energy states are basically random. I mean, can you say a little bit more why what you have in mind is different from the usual way?
Well, I don't know if it's different from the usual one, but I do think there's something special about gravity in that there's a UV, there's really a distinct UV part of it. This is the part that we want to be random. We don't want to treat even very complicated things in the low energy effective theory as random. And the difficulty in higher dimensions is understanding how to, for example, if you wanted to define an ensemble in higher dimensions, you would have to find the analog of a Virasoro block, which is like resumming all possible single trace and multi-trace exchanges of all the light fields. How do we do that?
Sorry, just a little follow-up. So earlier in the talk, you said that we're going to apply ATH for operators which are near or above the black hole threshold. But the near, which part is that? Is that the low energy theory, or is that the random stuff? I mean, if you think of it as a back-reacted particle whose mass you tune up, it feels like it's low energy, but I know you have in mind order C, so how are we supposed to think about that part?
Yes, good. So in 3D gravity, I know the answer to that, because in 3D gravity, there's a precise threshold for when three operators can make a wormhole or not. And the threshold for when you treat them randomly is when they can make a wormhole. So there's some condition on the three weights, H1, H2, and H3. In higher dimensions, I don't know the answer to that, or we don't even know whether there's a clean universal. There won't probably not a universal threshold like that, but we don't know how to separate the stuff that should be random from the stuff that should not.
Maybe you could turn it around and use it to define the small black hole regime in a more rigorous way.
Yeah, presumably the answer is the same in that if you can make a wormhole, then it's random. But that's not very satisfying. I don't know I don't know how to turn around.
Can you define an index that can measure this difference of the states that are running between P and Q earlier?
It's an interesting question. Not that I know of. I don't know. Sounds a bit like the distance of the particle from the horizon.
Yes,
I don't know.
Exactly.
I don't know.
Yeah. So your ordering was basically dictated by the OPE, the rate order in which you took the OPE. If you took the OPE in different orders, you would get presumably different areas. So in some sense, like, different apparent horizon sizes of Python launches. So these are different pictures of the tensor network.
That's right. That's right. But they are equal to each other.
Because they're just different channels in the OPE expansion.
That's right.
So I just wanted to make sure I understood this statement about the identity not appearing. Are you saying that if you rewrite this correlation function, but decompose it in a channel where you first fuse O and O dagger, then the thing that dominates in that channel is heavy states instead of the identity? Is that the statement? Yeah, that channel.
Can you see this?
Yeah. Probably.
Okay, so in the other channel, the question is what, so in the other channel looks like something like this. So if we were going to write a crossing equation, this would be the other channel. And it's true, whether or not the black hole is behind the horizon, it's true that these operators fuse to the identity, and you get the right answer for this correlation function. However, that has to break down if we allow for complicated stuff on the outside. So if we just insert some primary operators, then everything's fine. It's always the identity. But if we look at linear combinations of those correlators, then we get the wrong answer. That's the statement when something's inside the black hole.
Okay.
At the very least, you need R equals P.
Sorry?
At the very least, you need R equals P.
Yes.
Yeah, I think I'm still confused about the time dependence business. Is it true that, I mean, in your context, you need your apparent horizons to be extremal? Or?
Yes, it is.
Okay, so then you can't really tackle the time-dependent situation.
Exactly. We only know how to chop up the bulk on extremal surfaces.
Okay.
I'm wondering if you could comment about, in the case when it's not isometric and if the measurement is done inside the horizon. You mentioned that this substitution on the board, this sort of naive EFC calculation, still give you the right answer for most observables. Okay, could you comment on, like, what does it tell us about gravity, that it's doing its best to fool us that nothing interesting is happening, right?
Well, I think
what does it tell us?
I think it's telling us something that we already knew, which is that gravity is an effective field theory. Yeah. But it also is telling us something interesting, that when you have a black hole, that the validity of the effective field theory is controlled by e to the s.
Yeah.
The validity of how many things you can trust behind the horizon is controlled by the area of that black hole. We already knew that in the sense that we know that as you approach the black hole singularity, that area goes to 0, and we know that the bulk theory breaks down. But what the picture of non-isometric codes gives you is it gives you a way of quantifying that relationship even when you're not at the black hole singularity. And for example, there have been some recent papers by Pennington and collaborators where they studied reconstruction in non-isometric codes, and they're able to quantify they're able to quantify, for example, how many states does it work, and how complicated of a state do you have to make before you start to see it break down.
Yeah, thank you. We can talk more about it later. But, thank you. Yeah.
Let's thank Tom again.